Everyone from California. Thanks for joining us from wherever you are. So it could be morning or afternoon or evening, but it's great to have you all here with us. Hopefully you're joining for the Airbus and CNS webinar on synthetic aperture radar. If you're not, you're in the wrong place. But again, it's great to have you here. My name is Grace Flew. I am a research associate at the Center for Non-Proliferation Studies. I work on the East Asia team, and we work with new tools. And so this includes things like satellite imagery and remote sensing data. And so because of that, CNS and Airbus have this partnership where we collaborate on things like high resolution satellite imagery and synthetic aperture radar data. So today, this is what Lars and Catherine from Airbus will be talking about. Catherine is an application developer from Airbus Defence and Space. Catherine is working in Friedrichshafen, Germany, developing products and services using synthetic aperture radar satellite data. In particular, her focus is on enhancing change detection applications based on very high-resolution Terraza satellite data. She has worked at Airbus for 4 years since graduating from the Masters of Science in Cartography program at the Technical Universities of Munich, Vienna, and Dresden. Lars Peterson is an application development manager at Airbus, and he is responsible for the development of products and services based on very high-resolution SAR imagery for security and defense-related applications. He's a member of NATO working groups and coordinates SAR-related case studies together with research institutes and military customers. Furthermore, he has been developing and executing several SAR training courses in the field of image intelligence for MODs worldwide. Mr. Peterson is a graduated engineer in cartography and geomatics, and he has served as an aerial image analyst with the German Navy for 4 years, has more than 20 years of experience in the domain of IMINT, OSINT, GeoINT, and geoinformation. So before I hand it over to Lars and Catherine, just want to set some ground rules for this webinar. So if you have any questions throughout the presentation, you can go to the bottom of the Zoom screen, and there should be a Q&A button. So if you open that button, you can type up any questions that you have, and I'll be compiling them and organizing them so we can ask all of them at the end. If you don't have this feature or you're calling in, you can also email your questions to us at geofornonprowebmaster@gmail.com. So that'll be the same email that you use to RSVP for this webinar. All right, so if you are calling in, there is a visual component to this presentation. So if you're able to, it would actually probably benefit you to be able to see the images and the PowerPoint that Lars and Catherine will be talking about. But if not, we will also be recording this webinar and we'll post it on the Geo for Non-Pro page, hopefully by the end of today. So fear not. All right, so without further ado, I will hand this over to Lars and Catherine from Airbus. Thank you so much for joining us, and I hope you all enjoy the presentation.
Yeah, good afternoon here from Germany, from the beautiful Lake Constance.
Hello.
Catherine and Lars speaking here. So first of all, thank you very much, Grace, for the very nice introduction. We are very happy to do this combined webinar together with you. Basically, this presentation is divided into, let's say, two parts. I will just try to explain, let's say, some basic and fundamentals to understand how the SAR image has been or is created. And afterwards, we would like to show you some real, let's say, applications and scenarios where radar can be a very powerful tool to support the image intelligence work. So what I would like to start is just to show you that we are working with radar, which means we are using a certain long wave frequency within the electromagnetic spectrum. Usually these wavelengths are divided into different bands. That means we start with a wavelength of about 1 meter in the so-called P band, and go down until we reach the shortest wavelength within these radio wave segment of about 75 millimeters. We, with Terraza, our spaceborne system, basically use the X-band. So that means Terraza uses a wavelength of about 3 centimeters and a frequency of 9.64 gigahertz. So we are using radar, which basically means radio detecting and enranging. So we have our, let's say, own transmitter in space that sends out electromagnetic waves to the ground, and we just receive the backscattered signals that are coming from the Earth's surface. So basically, what we measure with radar is the runtime of a signal from space to ground and back to the radar sensor. So for that, we because we need to measure and we need to find the right spot on Earth, we have to use the so-called side-looking geometry, which is a little bit in contrast to the optical world, where you can also work with nadir images, and you have a so-called central perspective view. In radar, we always have a so-called slant-oriented view. So that means there's no way for us to look really nadir. That means basically that whenever we have a certain object with a certain height, like this skyscraper that we can see here in this radar image on the left-hand side, we always get an effect that is called layover. I will also explain a little bit more about that within the following slide. Basically, that means we get an impression of the side walls or the facade of a certain object, and this is overlaid over, let's say, the surrounding area. We can see here on the left-hand side, the look direction arrow shows that we are looking from top to bottom, more or less, and we can see that our building, let's say, overlays the nearby river. This is the layover effect that you always find whenever you have an object with a certain height. So radar images are usually black and white, and we also have a lot of gray values in between. And this is because we just measure the intensity of the backscattered signal. That means whenever a certain surface has a certain roughness, we get a certain amount of backscatter that is received by the antenna, and it is then transformed into a certain gray value. If a certain surface is completely smooth, and when we talk about smooth and rough, this is always related to our wavelength of 3 centimeters of the Terraza X wavelength, then this surface appears black. We can see a small image on the lower part of that slide. The left arrow shows into the dark area, so it's completely black. This is basically a very smooth and calm water surface, so there are no waves. That means that this smooth surface acts as a kind of mirror. So that means all energy is reflected away and no signal is transmitted or reflected back to the sensor. Therefore, these pixel values are very low, meaning they are black. On the right-hand side, we can see that there are some brighter and some darker gray pixels, and this is basically the landmass. And depending on the roughness of the surface, depending on if we just have bare soil or some vegetation, we have different backscatter values, and therefore also different gray values in this image. When we talk about backscattering, we basically have three main mechanisms where we can define what kind of radar signal we are observing in the radar image. The easiest one is just the signal bounce, where which means we have a rough surface. The signal just reaches the ground and is reflected back in the direct way. Then we have the so-called double bounce. This can always be found if we have a certain object with a height, for example, buildings or trees. Here we have two interactions between the outsending signal and the return of the signal. So that means the signal goes down to the ground, bounces to the front of the building, as we can see here in the middle, and bounces then back to the radar sensor. So this is called a double bounce. And the volume scattering always occurs when we have, let's say, a mix-up of several interactions between the radar signal and objects on the ground, like the tree crow or these lattice masts that they use for power lines. This is then called a volume scattering. To show you just some examples, here the typical dihedral return that we can find very often when we look at buildings, for example. As soon as we have a building that is built on a certain paved ground, we have two smooth surfaces, meaning the paved ground in front of the building and the wall itself. And then we get this very nice dihedral return, which is basically these white lines that you can see here on the lower right-hand side. So these white lines that indicate the foot point of the building. We just usually see one or two balls depending on the orientation of the building. That means just these two walls that are facing the radar. We can see this view arrow, which shows that we are looking from the right side to the left side. So these two buildings facing the radar are shown up with these nice white lines, and the wall behind this is covered by the roof, so it's basically hidden if we do not get any returns from this part of the building. So basically, when you look for buildings, try to look for typical L-shaped white figures. This is always a good indication for buildings. The next version, when there's a double bounce, there's also a multiple or triple bounce effect called trihedral return. Here we have three planes at a right angle, not at a right angle, with an angle, so that the signal interacts three times before it returns back to the radar sensor. So because of this interaction, you sum up several signals in one single spot, in one single point, and therefore these returns usually appear very, very bright, as we can see here at this SAR image on the left-hand side. On the top right corner, you can see a picture of these of the facade of this building, and we can see that there are several edges and corners, and all these corners cause a very bright trihedral return. And because this building has a certain height, we have a lot of them, and therefore they appear also as layover. So this is the reason why we get these very bright lines here in the center of the SAR image. This is basically the layover that consists out of several trihedral returns. So these kind of objects can be observed very, very easily in a SAR image. The next point that we also have in all images, as soon as we have a certain object with a height, is radar shadow. This is something that you cannot get rid of, because, as mentioned, we always have a side-looking geometry, so there are always radar shadow. We can just, let's say, minimize or let's say work with this radar shadow in changing the viewing angle, meaning we can change from steep to shallow incidence angles, and therefore can, let's say, modify or work with the length or the amount of the radar shadow area. Radar shadow means basically a no return area, means no information. So everything that is within this radar shadow area is just hidden. So there's no way to, let's say, by image manipulation or anything like to derive information out of this area. It's simply black, meaning no information. But there are also certain cases where the radar shadow can also give you some helpful information. And one nice example we can see here by looking at this power plant. On the right-hand side, we see these very, very bright returns coming from the different boiler houses. Then we see some, let's say, long and narrow shaped black lines. So this is basically the radar shadow of these 3 smokestacks, which we can hardly see, let's say, by using just the radar signals from the smokestack itself, because it's round shaped, so there's hardly any backscatter from the object itself. But the radar shadow helps you to identify the shape and the size of these smokestacks. Same effect we see for these Venturi cooling towers. Also here, because they are round shaped, they have a smooth material on the outside, so there's hardly any backscatter. But what we nicely see here in the radar image is the exact outline showing the Venturi-like shape in the radar shadow. So that means from time to time also radar shadow can be used as a helpful tool to recognize certain features. I already mentioned the effect layover. This is, let's say, the opposite of the radar shadow. Opposite means we do not have a no return area. We do have some returns. That's the reason why this layover always shows up. And the next opposite, let's say, point is that it always shows up in the exact opposite direction of the radar shadow. So the radar shadow is behind the object, and the layover is, let's say, in front of the object. Nice example we can see here. This is a small lattice mast, and we can see by looking from the left-hand side, the foot point is on the, let's say, on the right end of this white line, and the top point is on the left-hand side of this white line. And this is just because we are measuring the runtime of the signal, and because we are looking from space, so the distance between radar satellite and foot point is longer than the runtime of the signal between the satellite and the top point of the lattice mast. Therefore, the top point is closer to the, let's say, sensor than the bottom point. Therefore, this layover occurs and lies always in the direction towards the radar sensor. The next very helpful and also interesting point is that we have the opportunity or the possibility with radar also detect objects that are below the spatial resolution of the sensor. This example that we can see here is a very nice illustration for that. We see on the middle part of the slide, we can see the outline of a high tension pipeline, which is located here close to the shoreline. This can hardly be seen in the Google Earth image as well, but I think it's a little bit more easier to recognize in the SAR image. This image, by the way, has been acquired with 1 meter spatial resolution, so it's not that high. But the very interesting part we can see on the right image subset, because here we can see certain lines that are going across this water surface, and these are power lines. And in this situation, we do see these power lines because they are oriented perpendicular to the viewing direction. And this means by having these kind of scenario, we are able to detect even these really small sized cables with radar just by offering 1 meter spatial resolution. So this is also one very important point. We are not limited to let's say detect or recognize objects that are bigger than our spatial resolution. Here just a short summary to show you the different effects that we have, starting from the layover, as I just mentioned, going to the shadow part, and when you have a certain hilly terrain, for example, you can also get a certain effect that is called foreshortening, where you, let's say, get the correct view of a certain object, but not with the real numbers. So the length, for example, of when you go to the very right-hand side, the length of this slope is not exactly how it is in reality. Compared to if you work with layover, for example, you can always use the layover value to calculate the real height of a certain object. This is very accurate and can be done with layover, but this is not so easy, or I would say it's not possible to do with foreshortening. So this is also a nice giveaway. Layover and radar shadow both can be used to calculate the exact height of a certain object. Yeah, the benefits of using Terraza. Here with Terraza, we are offering the highest spatial resolution commercially available from space. That means we can deliver SAR data with a resolution up to 25 centimeters. And what that means, we can see here in this nice comparison. On the right-hand side, we see a SAR image that has been acquired with 1 meter resolution. And on the left-hand side, we use the same geometry and nearly the same situation on ground. And this image has been acquired with 25 centimeters. So we see the image on the left-hand side is much sharper than the right one. On the right-hand side, I would say it's really hard to determine what kind of object are we looking at. On the left-hand side, it's also not, let's say, that easy to see what we are looking at, but with, let's say, some experience and some image manipulation, we can derive nice information out of that. So if we just focus on these yellow square and we zoom in a little bit, we do some little bit of filtering with the image. And now we can see that we are looking at certain trucks, open cargo trucks. On the right-hand side, I put in a reference image that shows the same situation in Google Earth. So just using very high resolution optical imagery. And if you compare these objects, you can see that the appearance of the objects in the radar image are, let's say, not completely different to that you can see in the optical world. Of course, it will never look exactly the same as an optical image, but by offering this very high resolution, you can also work with certain recognition features that you also use by classifying or identifying objects in the optical world. So basically, we are looking at these kind of trucks in both images. Yeah, so just as a short summary, why should you use Terraza for image intelligence? One simple reason is we are using SAR. It's an active sensor. It works all the time. We are weather independent, so that means we are not affected by clouds, by different daylight situation, rain, fog, whatever. We can guarantee a certain information over a certain area to a specific time. We offer, especially with Terraza, up to 25 centimeter data, with its best commercially available data so far, with a very high precise geolocation accuracy, which is also unique, and because of the excellent radiometric stability. That means if you acquire a certain area with the same geometry after a certain amount of time, days, months, whatever, if nothing has changed on the ground, you will get exactly the same signal back. And this makes it such a powerful tool for change detection, which we will now see some examples afterwards explained by my colleague Catherine. So basically, what we see is that you can use radar also for image intelligence applications. We will show you some examples afterwards, but also the example with these open cargo trucks, I think was a nice impression what kind of level of detail you can expect by using with radar. Another side effect is also that you are able to detect moving objects if you use SAR data. That was it for the moment from my side, and now I would like to hand over to my colleague Catherine.
Okay, so I'm just going to switch our presentation. Let me see. So I'm going to give a brief introduction to SAR change detection techniques, and then I'm going to shortly give some examples from Sharud in Iran, where we've spotted some changes using SAR change detection. So Lars introduced the different types of backscatter that we receive from the sensor. And when we monitor these in a grayscale image, we receive, for example, a sort of speckled black and white mixed gray value for multiple reflection or volumetric scattering. For the water bodies, which are smooth surface, we receive no return. And for buildings or corner reflectors, a very strong return, that's a white high return. And for so rough surfaces, we receive something also kind of grayish. With this information, we know that we can detect very clearly changes between those backscatter. So if an area has changed from a bare earth to a new building, it's very easily picked up because it's a strong change in the backscatter, and that's what we call amplitude change detection. So, for example, in these two cases, this is two images from an airport. We see in time one, we can look around and flick between the two images. There's different techniques for doing this with visual analysis using overlay or using swipe methods. We can flick and see what the changes are. But the simplest way is to use either ratio or difference between the two images, and we get here the backscatter increase or decrease. So we're very clearly, we see where there's a change. In this case, on the hard stand, there's a new aircraft that's arrived. We can also overlay this information on optical data and quickly are alerted to where there's changes. So hotspots of activity or new sites, buildings, that kind of thing. So this is using the amplitude for change detection. There's, however, another method for change detection with SAR data, and that's exploiting the phase of the signal. And that's what we call coherence change detection. And in this example, we see that in this small sketch, that at time one, there was no change. Or in the reference scene, the surface was stable. In the second period, there's been either a slight decrease of the surface height, or if there was a movement on the ground, and we're talking in kind of relative to the wavelength of 3 centimeters, we're talking really small changes. And this change we can detect because there's a difference in the phase. So there's if we calculate between the phase of the two return signals, we notice a difference. This can be for natural reasons. In the case of trees that are volumetric scatterers, they would never produce the same signal back after multiple days. But in an area like an arid area, where nothing has changed, we would expect to receive the same phase back. So that means that if there is a change on the ground, it will be detected by the sensor in the coherence. So to show an example of that, at the same airport that we looked at previously, we can see here that that there's been, if we color coherence low as black, we can see here that there's multiple tracks that are very precisely running around this area of sand. Precisely why, or exactly why, we're not sure. Maybe you also have some ideas why exactly somebody would drive around like this in an airport area. But what's really interesting is if we look simply at the amplitude, as we did before with the amplitude change detection, we don't see this change at all. It's not visible. But yet, looking at the coherence, we really pick up this difference. So we have different benefits using the amplitude and using the coherence, but there's also the possibility to use them together. So what we can do is take the red, green, blue channels of an image and place the amplitude of both dates and also the coherence within those. And we call this multi-temporal coherence. So we have amplitude of time 2 in red, in the red channel, amplitude of time 1 in green, and the coherence between the two images in the blue channel. And this gives us an image like this, which is quite psychedelic at the first look. It's quite bright and colorful, but it provides really valuable information. So for example, this is, we have here 4 vehicles that you can see here parked between time 1 and time 2. But what you can interestingly say is that this vehicle here, the second one, was perfectly coherent between the two dates. So it stayed parked there, didn't move. These 2 vehicles that are green, they've disappeared. So they were only in time 1. And particularly interesting is these 4 vehicles that are yellow. They've been parked at both dates, but they've moved in between. So either they've been driven away and returned to the same site, or there's been some kind of maintenance that's taken place. And another example of this we can see here, looking at some helicopters just placed here. If we look at this in a SAR image using the amplitude only, we can see that between time 1 and time 2, this helicopter, the third one from the top, has arrived. The fifth one has departed. And looking at the coherence, which is what the first look is quite ugly, but it provides us with some useful information, that these 2 were completely coherent. So they've not moved between time 1 and time 2. And if we pack this information together in the multi-temporal coherence image, as we said before, we can say these 2 were inactive. This helicopter has arrived, this helicopter has departed. And interestingly is that this helicopter here, that was present at both dates, but incoherent, must have moved in between. So it's good for giving an indication of whether sites are active, or whether all the materials or vehicles, whatever the objects that we're looking at, if they've been moving, if they've been moved at that between satellite passes. So now I'm going to go into some applications or some examples from site monitoring. There are other examples, applications for SAR change detection, such as in the oil and gas industry or for environmental monitoring or for forestry, but for now we're going to look at just at site monitoring. And I'm going to use examples from Sharud. So we've been monitoring this area since 2016 through a collaboration with the image analyst Alison Piccioni, who guided us to look at this area. It's a space facility site. It's also potentially a missile test site. And as you can see, there's different areas that we can look at. So at the first area, the launch pad, we can, using this multi-temporal coherence imagery, we can quite easily detect when the gantry tower here, when that moves backwards and forwards along the railings that are here. So this is quite a simple detection method. What's perhaps more interesting though is when we see here around the outside of the launch pad area, and we can say that these areas where there's low coherence, these must be where there's tracks have been driven. Taking this one step further, we can say between the horizontal assembly building and the launch pad, there's a road and a fence that we can look at here. And what we can detect is, for example, here when there's low coherence, where, and this is, oops, that should be 2018, apologies, where there's been a trench that's been built. And we not only see that this trench has been built, but we see exactly where the workers have moved along the outer fence to gain access to this trench area. Then we see that this area remains coherent, so the trench stayed open for a period of time, and then most recently we see how it was then filled over. So it's reduced backscatter has been filled over, and also this area here where there were heaps of sand placed, we see when they're also moved back over the open trench. So it's a good method to see kind of like patterns of activity and how maybe construction is taking place, such as trenches or groundworks, before there's big structures or big buildings that are built. Similarly, using the coherence, we can look inside the crater area. So inside the crater here, there are 5 test stands. Here you can see that there's been a test, and you can see this kind of burn scar in the optical image. Looking at this in SAR, we can see here, this is at the end of October, end of 2016, October to November. We see also this dark area where there was this burn scar, and we see a number of tracks going to this area, and also going here into an underground facility, or maybe into some shadowed area potentially. What we can say though is in the next period, we can see how the tracks are maybe diminished. There's not as many now. There's no track here going to the site here. And going a step further, or in time, we see now when a new test has taken place, most likely at this test stand. So where this green area here is backscatter decrease, and this whole area around here of yellow is low coherence, so most likely some form of large energy or has pushed away the surface, brushed it smooth, and that's why there's a backscatter decrease. At another period in time, we see this more strongly at the second stand, and we see now on the left-hand side, this area state remains the same, so we can say exclusively that there was most likely a test at the second stand, but no activity at all here in the north. We also see here some pylons that have arrived since the previous year, so some cables, power lines. And yeah, so they're detectable too. And in the final time that I have here, there's we can see also here where there's most likely been sort of a turn of a vehicle around here and also driving into this area. Okay. And finally, I just want to show an example from the support area, which is in the west of the site. And just to put starting from 2017, we see really how this area has grown in size. So with this establishment of the new facilities here, also new trenches to maybe build particular infrastructure to those sites. And by using the SAR with the same geometry, which is very stable, we really pick up the changes, always changes that are on the ground and not from changes to the geometry of the satellite, for example. And the last point in time here at the end of August, we see a very long new trench, new construction, most likely a new road going up to the hillside here. So that's an overview of SAR change detection. Just to summarize, we can take two images. We can apply different techniques. So we can apply the amplitude change detection to detect new constructions and the movement of objects at a site. We can use exploit the phase information of the signal between two SAR scenes to see very subtle surface changes. And using these two methods together, we can detect activity between satellite passes, such as the movement of vehicles, the helicopters that I showed, and also the engine test potential that we showed. So that's a summary of change detection, and thank you for paying attention. I hope it was interesting. It gives you an insight into how SAR change detection can be used. If you have any questions, we'll be very happy to take them. If you think of something later, then you're welcome to contact us. You can also look on our website, intelligence-airbusds.com, where you can download sample imagery. There's also further information about case studies, and also like product specifications, that kind of thing. So take a look if you'd like any more information there. And yeah, we welcome any questions that you may have.
Awesome. Thank you, Lars, and thank you, Catherine, for your awesome presentation. To also remind all the attendees, some of these images that Lars and Catherine talked about, especially the ones at Sherwood that show the change detection, are all available on geofornonpro.org. So you can also check them out there, and you can also pin comments, and if you notice something that maybe some of us noticed, definitely go there and point it out for us. So we have just about 15 minutes to do some Q&A, and so we've already gotten a few really good questions, but if you think of any now, we're still taking them, so please send them in. You can use the Q&A feature on Zoom or email them to geofornonprowebmaster@gmail.com. So I guess we'll go in order that the questions were given, because it will go more with the flow of the presentation. So our first question is, SAR has been around for a while, more than 25 to 30 years, or maybe longer. So what has changed in the past 5 years or so, and what is changing that makes SAR so useful? Is it the resolution, or is it the data analysis, given the new computing power that has come up in the past few years?
I would say it's both, especially the spatial resolution make a big difference. We recognized it because in the first days of Terraza, we were just able to create 1 meter SAR data, and whenever our defense customers, for example, that usually look for small size objects, try to recognize or identify certain small objects like small aircraft or vehicles, they realized that this was not possible with the 1 meter data. So therefore, we implemented together with the German Space Agency to implement these 25 centimeter mode, and we saw a huge benefit of going below 1 meter. So when it comes to the classification results of man-made targets, this step below 1 meter was a very important one. So, but of course also the new computing techniques also support this. For example, these kind of change detection products that Catherine just showed for several years or a few years ago, that it took quite a long of time to process all this data, which nowadays is a really short time frame.
I would add also is very interesting at the moment is time series analysis and the launching of several new satellites. So, for example, the European Copernicus mission of Sentinel-1 satellite, so the availability of very frequent data, a lot of data. So that's really making a difference to time series analysis. Terraza X also has a new triplet that was launched this year, so the Spanish satellite PASS, and that's allowing really, when it's fully in operation shortly, then it will be allowing even a more frequent acquisition of or monitoring sites, and there's a lot more data and a lot more time series analysis.
Okay, so to follow up then, what is, I guess, the biggest challenge now to improve SAR collection capabilities or analysis?
The biggest challenge? I would say, I don't know if it's the biggest one, but at least it's a big one. We are facing always feedback from our customers that would love to see in SAR image that appears as an optical image. Yeah. And this is something where let's say a lot of work is been done actually, that several computer scientists and experts try to make, especially using deep learning techniques, to make a SAR image, let's say, looking like an optical image, to make, let's say, this data more useful to a bigger audience. This is, I would say, one of the biggest challenge we are facing right now.
Yeah, to move more away from the imagery to like an information level. Yeah, because I would say SAR is definitely like a measurement tool rather than always an imagery tool. So it's got very precise information, but to move that to more information.
Okay. So along those lines, one of the attendees was wondering, the phase changes, the coherence are able to slow slight changes in the absolute distance from the satellite sensor to the ground object. And it sounds like they're surprised at how precise these measurements can be, given that you have to calculate the satellite's absolute position in orbit to the ground within the measures of precision that these change detection algorithms use. So can you speak a little bit more about that? I guess it is surprising that we're able to calculate the satellite's position relative to the ground so precisely to where we can make and see these smaller changes. So I guess what is the scale of this change detection? Is it on the scale of meters, centimeters, even smaller?
Yeah, so it's phenomenal. The precision is, but the reason for that is the precision with which we can say where the satellite is. So it has a very high geometric accuracy because it has GPS and star tracker. I think it's got an unrivaled accuracy, and by knowing exactly where the satellite is and its orbit location, therefore we can say the exact distance to the ground and monitor that between two satellite passes. And so that this height change that we didn't discuss it at the moment, but there's a method of studying deformation. So looking at, for example, the surface movement of bridges, stability of critical infrastructure such as dams, and this is really in the range of like millimeters. So, and they use like a time series of data to really like build up that accuracy as well.
Yeah, that's just absolutely phenomenal. What we can do with the technology that's been developed, and to be able to manipulate that in order to pull insights from it. So then, given all this technology and how advanced it's becoming, and all these techniques that we're able to use, is it easy to fool or deceive SAR? And if it is, then what are some countermeasures that you can take to prevent this?
Yeah.
Can you repeat the question, please? Because the first part I missed a little bit.
Oh, sure. I'm sorry. So the question is it easy to fool or deceive SAR? And if so,
okay.
then, are there countermeasures that we can use to prevent either getting false information or false readings, or I guess getting the wrong insights from this data?
There are some methods, of course. One of the let's say one of the methods is that you just, if you try to hide something, let's say a small size object, you can, for example, put a large corner reflector just at the side, so that you will get these very strong trihedral returns, which basically means these returns would overlay the object that you're going to hide. This is one option, but this is, let's say, gives the disadvantage that if you point a very strong corner reflector in the image, of course, this will show up very easily. So you will recognize very easily that at least something is there. The other way is, let's say, to hide certain objects, and some materials like metal sheets, for example, do prevent, let's say, the recognition or the appearance of objects in a SAR image.
Okay. And another participant is wondering, when we're looking at radar shadows, how do you tell the difference between just a black smooth surface on the ground and a radar shadow?
That's a good question. And it's not always, let's say, very obvious. Of course, you need to look in the vicinity of this dark area. If you see, let's say, some kind of dihedral returns, meaning white lines or white blobs, this is usually an indication that there's an object here. So then, if you look at, let's say, the backside, when it comes to the viewing direction of a satellite, then it's very sure that this is radar shadow, because this is exactly correctly mentioned in the question. The pure appearance of a radar shadow and a very smooth surface are very similar. That's true. So that means you need to look in the vicinity and also look for certain backscatter in the object.
Okay. So then, given these nuances and these different techniques and strategies to look at SAR data and to analyze it, how long do you think it would generally take for someone to be able to learn all these techniques and to be able to effectively see types of, changes or notice these details in SAR?
That's a very good question. We get this question quite often. yeah, it depends on the level of expertise you would like to reach. I mean, if you would just like to detect, let's say, simple changes, as we have shown in these multi-temporal coherence, meaning the usage of certain roads. This is very easy because, as we have seen, you just need to look for certain line features that are that have a different color, meaning these yellowish green color compared to the surrounding blue appearance of the coherent surrounding soil. So this is, let's say, very easy to reach. If you would like to identify certain man-made objects like vehicles or certain type of aircraft, this will of course take you some more time to be able to recognize or identify man-made targets like that. I would say at least if you really work on a daily basis with high resolution SAR imagery, it would probably need at least one year.
Okay. I mean, sounds like something that you'd have to dedicate a good amount of time to. So you had also mentioned, with this analysis process that you do have some help with automated processes. So can you talk about this, the kinds of automation that you use to help you process and interpret SAR?
Yeah, so there's different like SAR softwares available, and we've built a processing chain that takes SAR scenes and input and like completes typical steps. So like co-registering the imagery is very important to be very sure that you're comparing exactly the same location in the image. Radiometric calibration, for example, and these steps. We've built our own workflow, but there's also a lot of information out there from like companies like Farscape, or from I spoke about Copernicus program. They also have their own open source software called SNAP, SNAP. There's a lot of information available on their website about how to build processing chains, which also takes, as well as Sentinel-1 data, takes data from other satellites, including Terraza X. So there's a lot of automation to build up this simple amplitude change detection, coherence change detection, and then the further steps of, at the moment, in interpreting that is the part that's manual, and that's less trivial to automate. But there are steps being taken to train signatures of objects, to train targets. Yeah.
Okay, that sounds really interesting, and those sound like a lot of good resources that attendees can look into if they're more interested in the automation process in looking at SAR. So I want to wrap up, and we'll ask one more question. I know there are several questions that we weren't able to get to today, but we will send them to Lars and Catherine, and hopefully if they're able to just offer brief questions, we can send out the answers to you, because there are a lot of really good questions we didn't get to. But to close out, one of the attendees says he is participating in the IARPA Mercury Challenge, forecasting military activity in certain countries and civil unrest in some locations. And he's wondering, can or has Terraza been used for these purposes? And if this is a sensitive topic, you don't have to, necessarily say where or when, but it sounds like it could be related to things that we've been looking at, like Catherine was talking about Sharud and other sites related to WMD. So at least from the CNS and Airbus side, we've been looking at locations like that. But Catherine and Lars, do you want to talk about any other applications to military activity or civil unrest that maybe Terraza X has looked into.
I missed the program, or what? I missed the details. Sorry, of what program were you talking about?
So it sounds like it's the IARPA Mercury Challenge, which looks into forecasting military activity and civil unrest in certain locations. So has Airbus looked into any sites or any activity related to this?
That's a good question. Yeah. I mean, usually we with Terraza we have a completely different concept. Let's say, for example, that the company Planet uses, for example, because they simply acquire images of the whole globe more or less on a daily basis. We don't have this capacity with Terraza. So we just acquire images where a certain customer or certain divisions inside Airbus task a satellite. So whenever, let's say, there's a certain need or a certain request for monitoring a certain area for, let's say, see some kind of preparation for troop movement or something like that, we can do that. So, but there's no, let's say, internal process where we regularly monitor certain areas. So one example is these huge military exercise that the Russians did just a few weeks ago with China, the Vostok military training. We got the information from open source intelligence, and we acquired a lot of images over this area just internally to, let's say, show some nice change detection products over this military exercise area. So that basically means, yes, we can acquire certain areas also with internal budget if there's a certain need for that. If this answers your question.
Yeah, it sounds like like Terraza X can give some insight into activities related to military exercises or activities such as these. And it sounds incredibly interesting what you're doing. And again, for all the attendees, if you're interested more into what we do here at CNS or what Lars and Catherine do at Airbus, please contact us through geo4nonpro webmaster@gmail.com. You also now have both Lars and Catherine's contact information. And like I said, we'll send the other questions that were unanswered and hopefully get back to you with some answers. So to everyone, thank you so much for joining us today. If you have further questions, email us. And yeah, it was great to have you all here. And thank you so much, Lars and Catherine, for your wonderful presentation on SAR.
Thank you from our side too, and hope you have a great day, afternoon, evening, to everyone that's listening. Thank you.
Thank you very much.
All right, bye.
Bye-bye.